Hi everyone, and welcome back to the Information Bottleneck. I am Ravid Shvalziv, and here with me my co-host Ellen, and our guest today is Max Welling. So if you trained a VAE, use a graph neural network, work with equivariant models, or thought about Bayesian deep learning, you've probably been building on ideas Max help put into the world. He's a professor for machine learning at the University of Amsterdam and the CTO and co-founder of CuspAI. He was the VP at Qualcomm before and also at Microsoft. So, hi, Max. Welcome to the podcast.
Hi, Ravid. Hi, Alan. Nice to be here.
So today we are going to talk about a lot of things, both in material science and AI, and like how you see the latest progress in the field. But I want to start with a very let's say open-ended questions. So Max, you've been doing ML for a long time, right? Long enough to have been several. This is the thing waves come through. So when you are now looking the field, what do you think in this LLM area? Are you happy with what we have been end up?
Right. Well, I'm definitely very impressed. I don't think when I started in the field, which was already long ago, 98, when I started, we trained models of maybe 100 parameters as a far cry from the trillions of parameters these days. And I have to admit that I'm constantly surprised by the insane amount of progress we're making. So I am very impressed. We are edging in on artificial general intelligence. You could argue that we are building things that are, at the cognitive level of humans. We can hold meaningful conversations with. At the same time, you can also wonder what is still missing, and and is scaling the right thing to do? That's something that's constantly on my mind. So we've seemed to, especially industry, has seemed to embrace the scaling paradigm because that's predictable. But if you see the enormous difference, like sometimes, between 6 and 8 orders of magnitude difference in terms of efficiency, energy efficiency for the same amount of intelligence between humans and current hardware, you think there is still a lot to discover out there. And maybe before we are sending data centers into space, we could also study the human brain and figure out how it how it creates intelligence, which apparently is a very different paradigm than the current hardware. So I think there's still a lot of really exciting things to discover. And so the field is not coming to an end, I would say.
So I want to start like, what do you think are the missing parts, or like what do you think I don't know, 5 years ago or 10 years ago, like what something that you would have bet or like that would have figured it out before we can get to the next level?
Well, I think one thing we are clearly missing is embodiment. So, but this is the next phase that's currently happening. People call it physical AI. But I think we will find out that it is also deeply related to the actual intelligence that we are building. So, I believe there's a whole spectrum of intelligences, and some of them are maybe self-conscious to some degree more than others are. Probably the ones we are building now are not, but it doesn't mean in the future we cannot build AI that is self-conscious. I don't see any reason why we could not, but it's probably an intelligence somewhere else on the spectrum. And I would expect that you would need to emulate human bodies and intelligence embodied in, maybe robotic bodies, or maybe even raising robots in the real world for that to achieve that particular piece. So I think that's something that's coming now. Also because I think we're probably going to run out of data, and robotic platforms are one way to collect a lot of data. And so that's a second reason why that's coming. And so that's one direction. The other direction is science. And so I think I'm a scientist because I started my PhD in theoretical physics, and I truly love science and theoretical physics. Um, and what has been very interesting is that, of course, AI is starting to make a big impact in science. I've personally, part of my career was about incorporating ideas from physics into AI, but now kind of the tables have turned and AI is sort of giving back to the sciences. And I think that is also an extremely interesting development. It also has a computational piece, which is trying to understand science at a very deep level. But it also has a data piece, which is collecting data out there in the real world through high throughput experimental setups or self-driving labs, and using those to improve the intelligence again. So I believe that is also a very interesting future development.
So when you look on, I don't know, at the scientific domain, what do you think we can say that will decide whether the ML is actually the right tool now? Okay, that like now we can actually apply ML to this domain.
Yeah, so there's a couple of things. The most important thing is that the data needs to be available for it. So there's certain applications where we can actually generate quite a lot of data these days. Like one clear example was meteorology, where the meteorologists have just stored their data. There's literally petabytes of data available in this domain, and that makes it a huge, successful target for a machine learning algorithm. So there's now quite a few very successful models out there which predict the weather. Um, Definitely like 4 orders of magnitude faster than PDE numerical integrators, but sometimes also even more accurately if you stay within the domain of where the data was acquired. If you go out of domain, of course, it's a bit of a different question. But that's one thing. Is the data available? And it can become available because people have done a lot of experiments, or it can become available because people understand the physics well enough. They can do, and the physics is simple enough so that you can actually simulate it. That's not always true because some problems are deeply quantum mechanical, and it's very hard to simulate, because if you have very strong entanglement, it's just very hard to find good approximations. But density functional theory is one approximation that is being used by chemists and material scientists a lot. That typically is good enough. And if you then throw enough compute at it, you will actually get reasonable large data sets on which you can start to train your machine learning models. So I think those are the two ingredients. You need to either get data by experiment, or you need to get data by simulation. And if one of those two creates data sets, you can start to train your machine learning models on them.
What's your definition of, because earlier you mentioned AGI. Do you have a definition of this, or do you think such words even matter?
No, I don't think the words matter at all. I think they are, in fact, very inflationary. I've heard the word superintelligence now a lot. I always wonder what's the next step up. I don't think they matter very much, but you could argue that the fact, if you sort of think of a simple Turing test, I think we're almost there, right? So if you hold a conversation with a chatbot, which is very advanced frontier model, the conversation is as informative as you would have with a human, at least on the sort of intellectual side, maybe not on the human side of understanding how humans work. Although I've even heard people have psychology discussions with chatbots. So I think if you take the Turing test, we are pretty close in a way to what Turing would define as AGI. But it's quite fluid, and I'm pretty sure there will always be people who deny we have reached AGI and people who will claim we have reached AGI, but it really doesn't matter, I think.
And what are domains that you think are like we will not get there soon? That like it can be that data is not available, or like I don't know, something fundamental in our understanding or our current algorithms. Do you think there are domains that you say, oh no, these probably we can't have good enough models?
Okay, so fundamentally, this goes back to the data question. Now, let's say if you have a problem where I think chemistry is actually a pretty good question, problem. But even self-driving cars are in that thing too. So if you have a problem where, let's say, there is a huge tail of exceptions, and you would have to collect data in all these exceptional cases, and there is not really like an abstraction that you can, where you can understand the world like humans understand the world, without actually generating the data for that particular case, right? So we understand the world in broad strokes. But if you ask me what the ground state energy is for a particular, molecule, I don't know the answer to that, right? To chemical precision. And the reason is, of course, that in order to access that piece of information, you will actually have to do the computation, which means you will actually have to invest the energy or dollar cost to actually do it. You could argue similarly with self-driving cars. I don't know where we get there. I mean, I guess humans can solve it, so I guess I'm pretty sure we'll get self-driving cars. But you could imagine there is application areas where, yeah. So the only way to get the answer is do a very costly computation. Otherwise, anything a human can in principle do, and where you can collect the data, I think a machine can also achieve the same performance. So yeah, so I guess materials is a good example. So like highly entangled quantum materials is a good example, like superconductivity. I'm not sure how hard this would be to solve.
Do you think? So, for example, like last week, we talked with Julia Kemp from NYU. She worked on math and AI, and before that, we talked with Sasha Roche from Cursor, that like basically they claim that like if you have a good verifier, right, both for math and coding, these are like two the best examples maybe, then you can high climbing on these verifier and just get better and better models. Do you agree with this claim that like as we are close to, like, as the domain is close to be like something that you can solve or can get signals with verifiers, then it will be easier to solve with machine learning and LLM in particular?
Yeah, that's clear because then you can apply reinforcement learning. So this is actually very similar to the way you do inverse modeling on materials. So you generate lots of candidates, and then if you have an easy way to verify whether the material satisfies all the properties that you want, you can then improve your generative models to make better molecules, right? So that's basically, you can generate your own data in a way. If the verification becomes very hard, like a quantum material, it's very expensive to verify whether that material has the right properties. At least in a computer, you could maybe do the experiment, but that's also slow and expensive. Of course, then it becomes much, much harder to train models on it. So I think that's kind of similar to what I said in terms of accessibility to data sets.
And what do you think are actually like, for example, for materials discovery, what do you think actually like shifted in the last few years that make it tractable? Do you think like these are the models, like our technological progress that you can actually like make these experiments?
No, well, there's a couple of developments. I think it's the chemists have become better in creating data sets. Like the materials project is one, but there's many other data sets now where you can train your models on. But I would say, on the other hand, also our models have become quite a bit better. For instance, the combination of graph neural networks and equivariance have created force fields, machine learning force fields. And so we've learned to put the right biases or the inductive biases in our models. And of course, now that at some point we have learned how to build these deep neural networks to make these very powerful predictions. That was about 2009 or so. And so once we knew how to do this and we developed a few other tools, it became also possible to predict forces and energies on these molecules. So it's data and advances in models and compute that made this possible.
Well, so you've been talking a lot about like molecules, and I'm wondering then, does your analysis change when you start looking at like biological data or even wet labs?
So yeah, so also in biological data, you often deal with molecules of many kinds, like RNA, DNA, proteins, and all these kinds of things. So some of these transfer, some of these things I said transfer nicely. But biology is far more complex than materials. So that's why materials is in some sense a very good application area because the physics is fairly well understood, except for certain things like high temperature superconductivity. I think nobody really understands why in the culprits this particular phenomenon happens. But the situation in a way is it's better and worse in biology. It's better because people have been very good at collecting very large data sets. So there's definitely clearly a much more concerted effort to create very large data sets. At the same time, the domain is far more complex. A cell in itself is already incredibly complex, and so there's a lot to learn. Many people don't really know everything about it, and so I would say that makes that field quite a bit harder. Also, I would say the fact that you have to go through certification and FDA approval makes the field also inert, slow, because it goes, before you have to test on humans if you develop a new drug or medicine. So that makes things quite slow as well, maybe less so in material science. But yeah, so the fields are a bit different. But yeah, but I think it's also a super fascinating field, by the way.
So maybe let's talk a bit about like the physical world, right? Because it's totally different, right? Like most of the people that's working in the machine learning field are working on, I don't know, it can be benchmarks, can be like some like other data sets, but they are not working with wet labs, right? They are not collecting their own data and spend months to collect it, and it's very expensive, and it's not clear like what you actually want. So maybe you can tell us a bit about it, like how this loop actually work. What are the time scale, like what you actually need to figure it out, like what is actually different from let's say classical machine learning?
Yeah, so this is a great question. And so this is something that is definitely very large on CuspAI's radar because we do understand that experiment is the ultimate kind of judge of what you have computed. And also the physical world also always produces a lot of friction. So, and this is like you set up an experiment. Now you have to build a machine. There's people, there's protocols for security. There is a physical location where people walk around. Those people may not trust your agent to tell the machine what to make, and so they will want to check, and that creates slowness. And then you figure out, hey, I need to actually buy precursor materials for my experiment. I have to order them, and it takes maybe a few months before you have them. And then you figure out I need a new machine, and it actually takes 2 years to get it. So everything slows down tremendously. So our approach has been to work with labs around the world, which are already operating and functional, where I would also say it's very important not to underestimate the difficulty of operating such a lab and the amount of domain expertise you need in order to operate such a lab. And so we love to work with the people who are doing this for their whole life already. And then we build trust. So we basically have our agent. We have an agent we call Mira, which is basically a workflow that generates molecules and evaluates them, basically designs them in the digital space. And then we connect that agent to a experimental setup. And there's different protocols of exchanging information back and forth that sets the material precursors as well as all the process parameter of the experiment. So the experiment, you need to mix in a few, materials. You have to decide on a temperature and a pressure and, drying time and whatever else you have for that particular experiment. So you need to set those parameters. And then the experiment runs and it creates data, and then the data needs to flow back into the model. And so there's kind of two streams. There is the digital simulation or AI accelerated stream, which tries to do as much computation as possible for you to recommend a particular experiment to do. And then there is the kind of the black box feedback from the actual experiment that says, okay, for this setting, I got this result from these characterization machines, and that data must flow back. And then you can also fit models to those. And the combination of those two need to come up with an optimal sort of experimental design. And ultimately, it's important that there's a new development, which is something that's very important in this field, which will accelerate the field forward, which is speeding up this experimental side of things. So there's now high throughput labs or self-driving labs, which are more and more gets roboticized so that the amount of feedback you can get from these experiments accelerates. And I think that is a very important piece because that's currently the bottleneck.
So what are the, like, you have from one hand, you have the simulators, and from other hand, you have the experiments data. How you, like, I don't know, balance between the two, like when you trust the simulator and when you want to run more experiments, how you actually do it in practice?
So this is a traditional exploration exploitation trade-off, right? So you need to have a sense of uncertainty embedded in your models to say, okay, here I have a very cheap model, like a property predictor, that gives you a window in which you think the relevant properties live. And then you go to a more expensive, maybe an MD simulator that kind of says, okay, it takes longer, the cost is higher, but the accuracy is higher as well. And then you go to DFT and it gets even more accurate. And then you go to experiment, right? And that should be even more accurate. And so there's a trade-off between the cost of doing and the time you have to do in order to get the data and the accuracy you'll get out of it. So now it becomes an optimization problem that is uncertainty aware. How much time should I spend on my cheap calculations and how much time should I spend on my expensive calculations and experiments? There is an optimal trade-off if you state, for instance, that if you state your objective, let's say I want, let's say I give myself a month to discover a material, but I want to spend the fewest amount of dollars to do so, or I have so many dollars and I want to discover the material as quickly as possible. Then there is an optimal design for you to navigate all these different tools you have available to you.
And how you deal, so in language modeling, right, a wrong answer is just hallucination or something similar, but in a wet lab, like the wrong answer or wrong estimation of some uncertainty is like wasted months, right? So how does this change your I don't know, your way that you think, or the way you design the experiments?
Sorry, I didn't quite get the question. So you say
How you, so my question is, like, you have like the cost of wrong results or like of errors for your models is much higher when you deal with experimental data, right? So there is something like specific that you try to avoid, or like is it like how you try to deal with that?
Right. So first of all, I think this is where the humans are in the loop. So they will check whether or not some very weird stuff is happening, like an hallucination will probably be caught by a human. Yeah, so if you do something that destroys your machine, maybe if that's what you're saying, then of course that's very costly. You should put in guardrails for this not to happen. But there's also a cost of not doing the right experiment, basically wasting chemicals and time on a machine by doing the wrong experiments. And of course, this is all a function of how good your models are and how good your optimization algorithm is.
And are you doing kind of active learning methods in order to optimize the speed and the cost?
We do active learning to get the right data to train our models to then do the experimental designs. So, for instance, for training force fields, you have an expensive let's say method to generate data, like a DFT calculation, and then you need to find the right structures to do these expensive calculation on to collect the data for the distillation to a machine learning force field or even a very cheap machine learning force field. And that is typically an active learning loop.
And why has active learning, I mean, maybe you would also, reject what I'm about to say, but it seems like active learning has not been that big of a deal in most of the modern, at least advancements with LLMs. Do you agree with that statement? And if so, do you have any beliefs on why that might be?
I know active learning is in my kind of experience more something where you would try to find the right data to label in order to train your models. I think you could argue that you know RL with human feedback is a little similar, where you would generate things and then you get feedback about what you've generated, and that would help you generate the next generation of things on which to get feedback. So that's also kind of inherently an optimization towards generating relevant things in the real world.
So you think that is there a general lesson here for ML for science behind materials, like, or does every domain have to rediscover its own loop and the specific details?
No, I think the loop is very, you can lift it to an abstraction level. I think there's a certain number of components. There is you set the objective. What do you want to make? Then there's typically a phase where you would look through your databases if it's already there in your data. If it's not there, there is a step where you would generate new designs. There's a generative model, which is kind of inverting, the analysis piece, which is if I give you a material or I give you something, a design of something, evaluate how good it is, right? And if you get enough of those examples, you can start to train a model that generates things with the right properties or approximately the right properties, so that we a generative model. And then, and then there is a stack of different evaluators going from cheap to expensive. And then there is a kind of a Bayesian optimization loop where you would use all the data and the different accuracies at which you actually evaluated all these materials in order to either generate more data that's relevant or to iterate to a particular objective, to optimize your particular objective like you actually do in Bayesian optimization. So I think that general design is the same everywhere. Like it's kind of the same inverse design that people use almost everywhere.
And do you think so? What do you think there is like? Do you think like there will be like foundation models that will eat science the way that eat in a language, or do you think we will have these separate like the same loop but with separate models?
I think so. So there will be people will train different foundation models for chemistry and materials. So we are training a foundation model that basically takes in the structure of the material plus maybe some features you can compute on the material, maybe run by brief simulation tools, or maybe even some experiments you've done on them, like maybe the outcome of certain experiments. And those will all be embedded in some abstract space, in a sort of a latent space, a code, if you wish, for that particular material. And materials which have similar functionality would live close to each other in that embedding space. And that you could call a foundation model, because from here you can predict forces, energies, and these are the machine learning force fields. But you can also use them to do other things. You can search in the literature maybe better. You can prompt your generative model. So there's all sorts of things you can do with that sort of abstraction layer where you represent your materials. I think that will be a sort of a, if you wish, a sort of foundation model across chemistry. But I think you will always find that if you dive into a particular subclass of problems, like a new material, you'll find that these models do not completely understand, these new materials, because every material is very different and you don't have data there yet. So you're kind of out of distribution. So you can kind of grasp the general maybe regularities, because it is after all a material, but the details are very hard to predict. And so you will then have to go through an active learning loop to find the right data points to fine tune your models for that particular material class. And so you'll get like a mothership of all, kind of foundation model for all of chemistry, and then you get a zoo of small fine-tuned models for each material class. And I don't think that will change very quickly in a way, because I think it's impossible, I think, to have one model that will basically understand all of it, simply because you need to invest energy and compute in order to get the details for every new material class. There is no one rule, except the rule is, of course, the Schrödinger equation. But you can know the Schrödinger equation, but you don't know the solution of the Schrödinger equation. You really have to compute it in order to know the answer for a new material.
Do you have any uh, oh gosh, do you have any opinion on like quantum mechanics in general, since you're bringing up the Schrödinger equation? And I mean, there's seems to be so much about interpretation of science that everybody seems to agree on. And in particular, how do you think AI will assist in development of, important things in quantum physics?
Well, we could be in for some surprises. I do definitely agree that quantum mechanics is a theory that is computational. We all know how to, well, not everybody, but most physicists know how to compute with quantum mechanics, so they know how to make predictions. But it is very hard to come up with a consistent interpretation. And every interpretation so far has certain aspects which sound pretty ridiculous. And so I suspect there is a deeper theory still that is more interpretable. And in fact, my former supervisor, Gerard het Hoofd, who won the Nobel Prize for his contributions to the standard model, even believes that there is a completely different interpretation that he's pushing. And there is no reason why sort of a very advanced AI could not become creative and sort of propose new solutions. In particular, I think humans interacting with these chatbots actually can come up with pretty creative new theories. So yeah, I think there's still quite a few things there to be understood, and I see no reason why chatbots and LLMs could not play an important role in that.
Well, and then speaking of chatbots and LLMs, what's your take on the concept of world models? And especially, I don't know if you've seen our podcast, or what's your take on like Yann LeCun's thoughts on that, for example?
Yeah, I think I'm a fan of world models. I think it's important to put the priors that we know about the world into these models. And I think there is this goes back to also what I said about embodiment. So in some sense, you need to put in every piece of knowledge you have about the world. It's kind of silly not to put it in a way, because it really helps you reason about the world. For instance, the fact that the world is three-dimensional is a very simple piece of prior and information, and the fact that the world has symmetries. Like if I rotate my head, the physics of the world don't change, or a millisecond after this moment, the world hasn't dramatically changed either. So there's a kind of a slowness prior. So there's all these facts about the world that we know. And, in principle, we could learn them if we have like exponentially large data sets. But why would we? Because we already know these things, right? This is also behind equivariance and the fact that you want to put symmetries into these models because they're there, so you should put them in. And so this idea about using the geometry of the world into these models will help you tremendously about reasoning about the world, right? I mean, if I ask you to solve a puzzle which is at its core geometric, it's just very hard for a model that doesn't understand geometry to solve that puzzle. Where if you understand geometry, you can solve that puzzle. So I also strongly believe that humans reason by I would say simulating a sort of abstract, very coarse-grained picture of the world forward in time in our brains, right? So, and that obviously uses world models, right? If I imagine, let's give an example. Like my child would be driving on a bike, and I would imagine myself behind a tree, and I would say, what if I would jump in front of the kid, like and scare it, right? we can all imagine what would happen, right? The kid would scream and fall off their bike, possibly, right? It's dangerous, so we don't do it. Ultimately, that is, if you imagine how you do it, it's really a very coarse-grained picture of concepts that's moving around that makes you understand the outcome of that. You don't have to do that at pixel level. And I think one of the things that Yann LeCun advocates is like, don't do these things at pixel level, do these things at these abstract levels where the number of bits is far fewer. And there you can already embed like lots of world knowledge. And so that helps you reason. So I think, yeah, I'm definitely sympathetic to that.
But do you think that it should be explicit? Because like Stefano was here a few weeks ago, and he said like, look, LLM, like it may be that like probably we want some like world model understanding, but we don't need to do it explicit. And actually, like current LLMs have it. They have it like in very like they just learn it from the data, right? So if you just force the model to learn something, and you have some like finite capacity, that's fine. Like you will compress whatever you need, and you don't need to do it in a very explicit way.
Yeah, so there's definitely the ability of models to learn these things, but you're making your life unnecessarily hard in a way. So you would definitely need a lot more data to learn this, and there's many things to learn. That's the other thing, right? So if you but ultimately, you could argue if you put the right prior in terms of compression. So you say, you know, I need to predict the future state of something, but I only have very few bits. It will create the abstract concept, which would correspond to geometry, because that's the best way to compress the data that you see. So that's probably true, but I don't see why we wouldn't put in the priors if we already know them, right? So that to me seems like a no-brainer. You know, put as much in it as you know. And the other thing I want to say is there's many things to learn, right? So there's certain things will definitely be learned, but there's also many other things which are probably quite hard to learn. And you would help it along quite a bit if you put in the right priors.
So why do you think, for example, in vision, right, like equivariance networks, or like even convolutional network, that like at the end it seems that right there was this big debate: do we need, like, is it better to use like convolutional networks or vision transformers? Like, and then it looked that it's very similar, right? It gives you like very similar performance. So do you think do you think, like, I see it as a good example of like, yeah, it doesn't really matter, you know, if you insert some priors or not, but in this case, do you think this is very specific to vision, or like the use cases that we are actually like tried these networks?
So I think there's a couple of things at play. So if you have enough data, you can learn these things. You can even use data augmentation for the symmetries instead of putting the equivariance in directly. Definitely, you can learn these things from data. Um, what did I want to say about this? I forgot. Can you go back to the question?
Do you think that, like in the vision case, that like we have a different, like that some methods are, that convolution networks are give us very strict priors versus vision transformers that gives us very
Yeah.
like non-strict priors? White matters, or like white doesn't matter in this case.
Yeah, so there's also this interaction with the optimization, I think, which plays a role. So if you constrain your space a lot, in terms of, let's say, putting constraints on the weights to create equivariance. If you do that, then you might make your optimization surface very difficult. And I think the optimization is actually very important. We've kind of learned this, right? So if you have to be able to do the optimization on your log likelihood surface or whatever, you have to do it really well. So I think there's something there where I suspect that if you would first relax the system and then slowly move in the right priors so that you've already reached a very good minimum, then I would suspect that adding the right priors, if they are true, I mean, they're not always precisely true, of course, but if they are true, they should improve the model performance afterwards. And you can sort of see it as almost like a pendulum, right? Where you know, one day somebody figures out you don't need the symmetry, or you can just use it by data augmentation, and then somebody else spends some time and actually trying to put in the symmetries, but then improve the optimization algorithm. And then they say, well, actually, it does help, right? And this is something that goes back and forth. In my view, if the priors are correct, which is a big if, of course, because sometimes they're not precisely correct, and then you might constrain yourself. But if they are correct, there should be a way to improve the models and learn the models with less data, but you will have to think very hard about the optimization algorithm.
And do you think there is a version of like a scaling hypothesis for science, or does the bitter lesson look different for it?
Yeah, there definitely is a scaling law there too, in the sense that if you add more data, the models will keep performing better. Now, I'm not sure we're at the regime yet where we have so much data that just throwing bigger models, bigger and bigger models and bigger compute will always work. But definitely, if you look at the recent work by Meta, these are very large data sets that they have created, and they are also training very large models. And I think in that regime, you also see just the same scaling laws as you see in the language and vision.
So if you had to bet in like 10 years, like what is the best model for predicting a molecular property? Will be a equivariant network or some general foundation model that just use the data?
I think it will maybe not so much. By that time, we have generated so much data, I would think, that the model architecture is not going to be of huge influence. So a general well-scaling architecture, the transformer of that age, which doesn't have to be a transformer, but I think the transformer of that age paired to the hardware of that age is going to be the leading model. It's only when the data sets are not very large or in sort of specific domains is where these kind of priors are going to be really helpful. I think this brings us to another really interesting question. Are transformers going to survive the next 10 years, right? Is it going to be transformers all the way? And I think we might see a surprise there that at some point somebody will figure out a better way to build layers into a neural net. The only problem I see is that transformers and GPUs are kind of really well matched. And so what you see is a co-development of transformers and GPUs and transformers and GPUs, and they're kind of co-evolving. And so if you come up with a new model or a new way to sort of a new layer, a neural network, you will not get the bold numbers. And so then the much slower process of also getting the hardware for that will also have to co-evolve. And so it will have to take some patience for people to break out of this paradigm in a way. And so I think this is very interesting. But maybe at some point there is so much pressure on like the economics of machine learning in the sense that it becomes so expensive. And maybe people want to scale it down to smaller and smaller devices, that there is actually a push for different hardware and different algorithms that would run on that hardware. And I would think there's going to be some very interesting developments there in the future. There's some companies that are actually building all sorts of either neuromorphic hardware or unconventional AI is a company that makes sort of more analog hardware. And once that's successful, I think we can also build very interesting new models and sort of neural network layers in those.
Well, so speaking of some of the startups, CuspAI seems to have this focus around like climate change. And I'm just curious what motivated this kind of framing.
Well, more or less, the framing is I'm very worried about the climate, and so when I stopped working for Microsoft, I had a good time to think. And obviously, I'm not the youngest. My hair is getting a little gray, and so I have maybe 10 to 15 more years of paid jobs. So, what do you do with the last piece of your career in a way, right? And I think it is very motivating to me to work on problems which have really positive impact. And there's many super fascinating problems in this space. There is a climate change is just one problem. The energy transition is another one. So there you talk about photovoltaics. So there's new developments where people make perovskite materials, which they layer on the silicon layers in order to capture more of the light, the bandwidth of the light. But there's also, of course, batteries and fuel cells, and even eventually also fusion and all these kinds of things. So there's a lot of really fascinating, also scientific problems in this space. And also, I would say it's of strategic importance to Europe, and to companies, to countries in the world to become independent of oil. So we are now in a situation where it gets increasingly hard to get oil, and oil gets very expensive. This is bad for many people, but it's good for the climate because we may actually push harder for sustainable energy sources and push this research further. So yeah, so I would say it's just very motivating to work on a problem that is meaningful and makes the world a better place.
So what you actually want to do? What is the goal?
For what?
For climate change, to predict it better, to have better energy sources, what to make it more efficient, what is your goal?
Right. So we started with the problem of capturing carbon dioxide from the atmosphere. So we are currently pumping about 40 gigatons a year into the atmosphere. That's about 2 lakes of Geneva full of carbon dioxide. And we have committed to being carbon neutral by 2050. It's of course quite doubtful whether we make it, but let's say we make it. Then after that, there is a century of removing carbon dioxide from the atmosphere at about 20 gigatons a year, half of the emission rate right now. That is a problem that we haven't solved because removing carbon dioxide from the atmosphere, as it's extremely dilute, is very energy intensive and very hard, in fact. So that problem still needs to be solved. And if we don't want to push that problem and the cost of that problem to the future generations, which is our children and grandchildren, we'd better work on this now. So that's the problem that we started off with. Right now, we also have problems in PFAS removal from water sources, so that's more a clean environment. And we work on fuel cells, which are basically for clean, I would say, ways to store energy, and also for cars and trucks to drive. So there's all sorts of fantastically interesting problems in this space that will help the energy transition and remove the carbon dioxide from the atmosphere.
And do you think is a common solution for all these problems? Or for example, I don't know, Frankfurter with Tab TFN, right? He has a solution and now he just come up what are the problems that we can solve with this solution? Or even Yann, right, with JEPA. So what is your direction? You first come with a problem and then trying to solve it, or
Yeah. So I think there is a general abstraction platform. This is the platform that we are building. So the platform in principle works for every material class, but every material class also has its peculiarities. So in other words, if you are going up the stack, which means in an MD simulation you can do for every material clearly. It is almost the same MD simulator, except for maybe the force fields that you're using are different. But if you go to if you build a digital twin, that digital twin is very specialized for that material, or even for the manufacturing or the reactor or whatever that process is living in, or the device the process is living in. And definitely, if you go up to the experiments, also these are different experiments for every material class. So that's not a sort of a solution that would work for every possible material class. So there is things which are abstract and transfer between the different material classes, and then there is bits and pieces which are very specialized to material classes.
And for working on the climate, do you think that I remember that a lot of the climate alarmist kind of stuff that I heard, especially in college, was talking about if we don't do anything, we're going to have all of these very catastrophic scenarios, loss of keystone species and etc. Are there any particular scenarios or like do you feel like a certain desire around this that kind of has a certain urgency, or do you think, for example, with the rapid rise of AI, that maybe we have these other, I don't know, like gray goo type scenarios? I guess what I'm trying to ask is like where do you think the risk of human extinction comes from?
Well, that's a big question. The risk of human extinction comes from humans abusing powerful tools like AI, and not paying attention to the damage they would do to their environment, to their own planet. I think that's where that real risk comes from.
Okay, pretty simple answer, I guess, but it makes
But
sense.
it's a big one. I mean, there's many ways in which it can obviously go wrong. But it's in a sense it's also a political question, right? So it's the question is, will we be able as a species to work together in order to put the regulation in place to make sure that these bad outcomes don't happen? That's, I think, the real challenge. At the same time, I also think individual researchers need to think about their own responsibility in this space. So work on problems which are, at least work on applications which will make the world better, and avoid applications which are obviously bad for this world. But that's a very personal kind of evaluation you have to make. What falls in one category and what falls in the other category. The one thing I do want to warn for is not to think about it. So if you don't think about it and you just do whatever, I think that's not a very good outcome. So you should at least give it some thought. What is your opinion about this? And then make a conscious decision of what you're working on, and then work on that. I think that's I think that at least we can ask from our scientists.
But what is your take? So, like in the past, there is a huge debate about safety and and risk of AI, right? So, like some researchers and other people also like claim, yeah, we need to stop everything. We need to write to stop research for 6 months or something like that in order to reevaluate the ways that we are measuring the risk in current AI models. And other people said, we need to wait to the actual problem, and then we will find ways to solve it. What is your opinion here?
So I think it is unrealistic to think that you can stop these developments. So I think maybe it's good if everybody stops at the same time, but this is completely impossible, right? I mean, it's like if one company stops, the other company won't stop. If one country stops, the other country won't stop. So I think that's completely unrealistic. I think what we can do as a community is pick the right problems to work on. I wouldn't say we stop working on AI. Just stop work on applications which are clearly bad for this world. That would be my advice. But otherwise, I think it's hopeless to see, because we are basically in an arms race, and the dynamics of arms races are that people race to a solution, or to race to be first. And that means you don't stop.
But how you think we should deal with models and some companies that claim they have such a strong model that can destroy the world, find some bugs in very fundamental systems? Do you think we should have some, I don't know, government regulations or self-regulate these companies?
Well, let's put it this way. Every technology is regulated. If you step in a plane, if you take a medication, if you take drugs, it's highly regulated. If you step in a plane, it's highly regulated. Everything is highly regulated except AI. So it makes absolutely no sense to me that we don't regulate AI, which is going to be the most powerful technology we have, right? So yes, of course it needs to be regulated. There's no doubt in my mind. It can be extremely harmful, and it has already been quite harmful to young people that are on social media or something like this. So, so we need to regulate. At the same time, we need to regulate in a way that is not creating an enormous amount of bureaucracy, so that startups cannot do anything. So that's the challenge. Do the regulation smart in a way. So yeah, that's my opinion.
But
about
how
that.
you think we should do it? I don't know. Do we need to have some I don't know, people that test these models before like companies release them, or like to regulate the use case of these models? What is the right way to do it?
So I find this difficult to answer because I'm not in this field, right? So I don't have a very strong opinion on precisely, how to regulate this field. I think self-regulation is hopeless. For the same reason as I just said, which is, we're in an arms race. So everybody, people don't constrain themselves because your competitor can go faster, right? Now, yeah, you have to be careful if you build a super powerful model that can completely disrupt, like software, as like with this new anthropic models. Then it's best to be very, very careful about this. So good thing Anthropic is being careful about it at this point. But it would be better if there would actually be regulation around this kind of stuff, but there isn't. So I think that's something. It's also very hard because regulation goes at a snail's pace. It goes very slow, and technology, it is just develops super fast. So I think if we want to even do it well, we need to figure out how to regulate fast. Instead of slow. So I think it's a very difficult problem to solve, but I think we need to get to it. It's important.
And who you think are the people that actually need to come with the solutions? Do you think the people that work on this model? Do you think I know some professors that working on economics or like social science and political science, or like maybe the like people in the governments? Like, who you think are the people that need to actually construct these solutions?
Well, I think it's regulators and lawyers that need to do it ultimately. The problem is that regulators and lawyers know very little about AI. So
Yeah.
you need to create I sometimes call this a rapid response team, or some kind of team. Like for COVID in the Netherlands, what we had was a rapid response team, which is basically a team that would assess every day the situation, where did the virus go, measure everything, etc. And they would recommend ways to the government of dealing with it. I think something like that we may need, which is a scientist who monitor what's happening everywhere and recommend measures and regulation to government. But then, of course, the government will have to learn how to very quickly pass laws and not take years to do it.
Okay, so let's maybe talk a bit about your book. You just recently published a new book, right? Generative AI and stochastic thermodynamics. Do you want to tell us about a bit about it and why you actually wrote this book?
Yeah, I'd love to. So it's not quite out yet. It's on pre-order, but it will come out soon. And so the idea actually started when I was teaching at African Institute for Mathematical Sciences in Muizenberg near Cape Town, South Africa. There is a very good AI for Science master that's being run there. And by Ulrich Paquet, I think is the most important person that runs it from DeepMind. And so I was teaching there, and so the topic of the book is the deep relationship between a theory in physics which is called stochastic thermodynamics, which is more or less non-equilibrium thermodynamics, and generative AI. And I think the easiest example is, for instance, diffusion models. So in a diffusion model, we start with a structured object, like an image, for instance, and we slowly disintegrate it into noise. So that is unfortunately the way life works. If you don't feed yourself, you will disintegrate into noise. And then we monitor this process, and then we try to play back the movie in the other direction. And if you play back the movie in other direction, you need to apply forces. And in thermodynamics, this means you have to do work on the problem. So you have to use energy, which is, we do this by eating and sitting in the sun and all these things to get energy into our bodies that will maintain the integrity of our body, right? So it will not fall apart. And so for these diffusion models, you will have to put energy in. Those are the extra scores and the functions which you have to run in order to invert the process. And so that's a very clear sort of analogy there. But I found that the mathematics between those two are actually almost identical. There is a free energy for both of these. In physics, we clearly have a variational free energy, which says how objects relax, for instance. And in machine learning, we also have a variational free energy, which is the elbow, evidence lower bound, which also is exactly has the same terms in it. And you can map the EM algorithm, which is expectation maximization, where there is an inference step and a learning step. You can map that to an entropy production or heat generation step, is inference, and a work step, which is the learning step. So there's these very beautiful analogies between the two. Yes, I've worked this out, and then I discovered that there's many more of these almost literal translations. So there is something called the Jarzynski equality, which is equivalent to what we call annealed importance sampling. And then there's these escorted free energies, which is called the stochastic normalizing flows. So we've kind of discovered the same algorithms in both of these fields, which I find fascinating. And at the very root of this is the fact that probabilistic AI is a theory about what do you do if you lose information or don't keep track of information, of all information, right? Because you basically use probabilities to describe all the information you've lost. And thermodynamics is also a theory about, what happens when you cannot, keep track of all degrees of freedom and you lose information in the process. And therefore I think the mathematics of both of these is actually the same. And I find that fascinating because now you can cross-fertilize.
By the way, so like as a student of Tali Tishby, I'm a big fan of compression. But do you think compression, at least in the more classical way, is actually useful today in AI?
Compression in AI, yeah, because clearly, because compression is a way in which you destroy information, similar to diffusion models. And it will help you extract the abstract concepts which you need to describe the system at a higher level of abstraction, right? So there is a number of organizing principles that will explain the world in these kinds of coarse-grained concepts and that are very, very useful to reason about. Now, something very similar is true in physics. In fact, we also wrote a paper about this, which is called the renormalization group approach. And in the renormalization group approach, you iteratively average out degrees of freedom, and that sort of changes the system from a very detailed system, let's say pixels, to a system of chairs and tables, right? And I see the information bottleneck in a very similar way, which is as you are going through the layers, you're adding more and more noise, which means the model is forced. A lot of bits get lost, and it's forced to encode the most relevant and important concepts in the few bits that are left.
But do you think, like, at the end, do you think we actually will use it in practice? Because there are many attempts to inject noise in order, again, like the principle is the same, right? That like we need noise in order to learn, to generalize all these things. And there are a lot of attempts to actually do it in modern deep learnings. And at least in my perspective, it didn't actually like give us better results.
Okay,
Like,
that's a good problem to dive into Bayesian deep learning. So I've been working with one of my students, Dario Korsha, a bit about this. And so one of the recent results he had, it will be published very soon, is that if you take an LLM and you do LoRa, right? So he developed this concept called BaLoRa, Bayesian LoRa, in a sort of a sophisticated way to add noise to the LoRa sort of low rank matrix. And he found, so we started doing this because we thought, well, it could help us get better uncertainty prediction. But he found that if you add this noise and you learn how to inject noise, you can actually train these LoRa models better. So it's just even a better learning tool. And so here you can see a clear example how if you inject noise in the right way, in this case we learn how to inject noise, it can actually not just give you uncertainty, but it also give you better learning dynamics.
And so do you think in general, like you worked a lot on, let's call it like foundational science, right? And trying to explain or come like with some underlying principles. Do you think, what is the role of these principles in today AI? Do you think this is gives us some like guidelines or like specific tools, or like maybe just we can get inspiration out of it? What do you think is the role of these basic foundation
I think
principles?
science progresses by having deep new ideas and then scaling those ideas, right? So scaling will get an idea, incrementally better and better, but doesn't fundamentally change the idea. And then you need the Einsteins and the people that are decorrelated from the paradigm and are willing to try bold new ideas to come up with something totally new. And I guess currently, we're not doing enough of that, and definitely from physics, from the very deep principles of physics and mathematics, we can get inspired by coming up with these new bold ideas. So one thing I've been working on with a bunch of students, in particular Andy Keller, did his PhD on this, which is the use of waves in computing. So if you think about, if you want to transport information over long distances or in time, like if you want to reason about something, you have to hold information in memory for a long time. Then models that do diffusion, they lose information. It's very easy to lose information because if you think about neural networks as maps, there is a phase where everything gets kind of contracted to a point, fixed point, and there is a phase where everything sort of explodes in chaotic behavior. In both cases, you lose information about the input. Holding on to information is actually very hard. And so there are some papers that basically say you should sit on the edge of chaos. So the dynamics should be fine-tuned to be not contractive nor too expansive. And it's interesting to note that the universe has solved this problem in a quite different way, which is by waves. Because if I want to learn something about the stars, right, I monitor waves like light and radio waves, etc. So waves really can travel very long distances and hold the information there. And recently, it's also found that the brain also actually communicates by by waves. So people have found by using different recording mechanisms like arrays of electrodes instead of single electrodes, they found that information actually propagates over the cortex with traveling waves. And people are now finding, what is the function of this? And I would predict one of the functions of this is actually to propagate information or to coordinate information between brain regions. And we've been working with Terry Sinowski and Lyle Miller, for instance, to try to come up with models for this or match the machine learning, which actually is related to symmetries, turns out, and the neuroscience together. And very soon, hopefully, there will be a neuroscience perspective paper, nature perspectives paper that will come out on this topic.
What do you think in general about the connection between neuroscience and ML? Like I did also like my PhD with Chaim Sompolinsky, and at least back then, like it was very like separate, right? Like you can collect like, or someone will collect you like, I don't know, 30 cells or like recording from such cells, and based on these cells you can develop some theory and you can feed the theory to the actual behavior. But it was very local, very I don't know, not big data, if you want to call it like that. Do you think that like we are in a better position these days?
And that's because we collect more data, because code loops back to the beginning of the discussion, right? Experimental data is at the foundation of everything, because if you don't measure things, then you won't see things and you won't even get the ideas, right? And so these days, people are able to collect massive amounts of data from the brain. And this will definitely inspire new theories about the way sort of brains process information. Now, I do want to say that NeurIPS, the Neural Information Processing Systems conference, in the beginning, it was actually a mix of cognitive science, neuroscience, and machine learning, AI. And this was very inspirational because you could really learn from the neuroscientists who would sort of discover all sorts of things about the brain. Recently, it's been much more deep learning and engineering. And we are losing a little bit kind of this part where we try to shift the paradigm. We really try to change the way we think about machine learning. I think, and that's a pity. So I think we should. I predict the next wave of innovation will come either from another insight from neuroscience or maybe from some physics theory that we will try, and we'll find actually, okay, this is the way maybe machine learning could be boosted, and then maybe that will change the way we do things.
And I'm glad you brought up NeurIPS. I'll point out ICLR is about to happen in Rio de Janeiro, Brazil. Do you have any anything interesting to say about conferences, especially the last several years?
You're a keynote speaker there, right?
Yeah.
Yes, I'll do a keynote. So maybe hopefully you can see the keynote. I'm making the slides as we right after. You know, I'm scrambling to get the slides together. Yeah, so I would say the conferences have become very, very big. This is, of course, a testament to the success of the field. At the same time, I personally like small meetings with excellent people and having deep discussions. And so, but you know, these meetings are also, of course, you just have to find them. But so these very big conferences, even I can get a little lost so now and then. I cannot imagine if you're just new to the field, you enter in this huge crowd, you know, how you feel. But it's yeah, so this is it's just become enormously large, and yeah, you wonder whether that's the. Actually, I enjoy the workshops the most because the workshops are of the smaller, more dedicated topics. Yeah.
And what you recommend for someone that new that comes to the conference, what to do? Like, how can you find the right papers, like the right people to talk with?
I think you're asked the wrong person. You need somebody who's young and knows how to do these things. I just walk in and I just bump into people. But I mean, there's pretty good tools, I guess, to find yourself the right papers. And then, but even nowadays, finding a poster in a poster session is like, you know, you have to walk for 10 minutes to get to that poster because there's like 1,000 posters or something. It's completely nuts. I don't think that's the added benefit of a conference in a way, because you know you can just there's excellent videos, and you can even talk to Claude or ChatGPT, whatever, or Gemini to talk about a particular paper. You can just get your information that way. I think the best way is finding people. So trying to find people that are interested in the topic that you're interested in, and starting collaborations, because collaborating with someone on a topic is, I think, the most fun thing. And in workshops, it's just the easiest way to find people that are interested in the same things as you are in. Yeah.
Okay, I think we are out of time. Do you have anything that you want to add, to sell, besides your book?
What I would like to sell is, well, I could say, if you're interested in joining CuspAI, we're always looking for excellent people. If you're looking for a meaningful job, we have a very good culture, and we work on meaningful problems. And
in Amsterdam? Or do
well,
you
we
have also in the state?
Yeah, so we have offices in Cambridge, we have office in London, we have an office in Amsterdam, we have an office in Berlin. And these days we're also expanding in other regions in Asia and the US. And so, yeah, if you're interested in working on material science problems in an awesome group of people, then send me an email, and we will talk at ICLR possibly.
Yeah, sounds good. I totally recommend to to go to work with Max. So thank you so much. It was a pleasure to talk with you.
Yeah, thank you very much. It was a very pleasant discussion.
And good luck. Thank you.
All right. Okay. Bye-bye, guys.